And what I want to talk to you guys about is this is a really good example of an exam problem, okay? Because what it's doing on this page here is they're introducing you to something that you've never seen before, okay? When I picked up the exam, I'd never heard of it before either, all right? And there will be questions like this in the exam. What I want you to do is read it, comprehend it, and then apply it. So that's the trick, is they're testing you on comprehension as well. Can you understand this new mathematical thing? It's not overly complex. We can read through it, and let's describe what it is. So we've got figure 10 is a box bounded by graphs A of x and B of x. Okay, so here it is, and we've got AX and BX looking like that, and it's 6 units squared. Okay, 6 units on the x-axis, 6 units on the y-axis. And the shaded region is telling us the constraints of it. There's the graph. Then we've got a Monte Carlo experiment. Okay, so something we've never heard of before, but they're going to tell us about it. Can be used to estimate how much of the square is shaded, and hence estimate the shaded region. And the way they do that is it generates 3 dots randomly, or it generates n dots randomly. So step 1, independently randomly generate a sample of n points within the square. Count the number of points that are in the shaded region, and then the observed value of p is going to be the number of points that are in the region divided by the total number of points. Okay, and that's going to be an approximation for the area of that's shaded. And we know this is going to be true, of course, right? If you put a dot on every pixel, that's going to tell you the exact area of what's shaded. If you only have 3 dots, like we do in our first experiment, it's a rough indication. Like if you looked at that, that's about a third, a little bit more than a third maybe, about a third. So that's what we're doing. That's what the Monte Carlo experiment is. Okay, so first question is, do we understand the context behind this question? Are there any issues with that? Okay, so that's what they're going to throw at you. So you know, with the exam, I've taught you all the skills you need. This is something that, like, you know, it's not written in the curriculum statement. Okay, so it's just going to be something that you have to read, comprehend, and apply. All right. So, and then we've got the shaded area is just going to be whatever p is times the area of the square. Okay. So then we've got a Monte Carlo experiment is conducted using 3 randomly generated points, and the results are shown. So we have 1 up here, we have 1 here, and then we had 1 out here. So we have 3 dots, and we had 1 in the shaded region. So part I, calculate the value of p hat. P hat is 1 out of 3. There is 1 dot in the shaded region out of 3 dots in total. Hence, show that the results from this Monte Carlo experiment indicate that A is 12 units. Well, A is equal to P hat times the area of the square. The area of the square is 36 units in total. And so we've got a third times 36. We've got 12 units squared. All right, so we're just saying how many are shaded. So we've got this proportion, this many are shaded, and there's 36 units in total. So how much of the total area is shaded? Well, 1 on 3 times 36. That's how we're generating that. Part 3, state why it may be inappropriate to construct a confidence interval for the proportion of the square that is shaded when using a Monte Carlo experiment involving 3 independently randomly generated points. So the question is why, like based on the information we have here, why should we not construct a confidence interval?
Because you only tested 3 values?
Correct, yeah. And so the best way to describe that is use this language, isn't it? N is not sufficiently large. And that would be perfect. Okay, sum size of 3, too small. We need way bigger sample. That's what you're saying, isn't it?
Oh, yeah.
Yes. Okay, very good. Send the page. And we have a new experiment. This time, 1,500 dots are slammed on this diagram here. And of the 1,500, we won't do 1,500. Of the 1,500, 600 of them are in the shaded area. Okay, using this information, fill in the boxes below to form a 99% confidence interval proportion of the square that is shaded. So it's a proportion and it's a confidence interval for a proportion. So that's going to be the observed value of P. Take the value of Z alpha on 2. So let's speak about it in terms of 95% confidence interval, because that's the one we went through explicitly. That would be 1.96 times the square root of P Q on N. Okay? So you can see we've got 2 boxes we need to fill in here on the left, and then 2 boxes we need to fill in here on the right. Now the first one is, this is for a 95% confidence interval. The value, we call it the value Z alpha on 2 is 1.96. Remember we looked at these different values. For a 99% confidence interval, does anyone have it written down? Or I can show you how we're going to calculate it. Okay, the way we calculate it is we go into inverse normal distribution. Okay, we set the area at 0.99. We're talking about 99% confidence. The tail is centered because we want it to describe the center of the distribution. We want this to be 99% of the area. So the tail is central, and it's a Z distribution. Standard deviation 1, mean 0. You do that, put that information in your calculator, and you generate the value 2.576. You've got 4 figures there, just to maintain a bit of accuracy throughout this calculation box. Okay, so what we're going to put in the first box then is we've got 0.4 take in the first box. I've written 2.576. Okay, that's the value of Z alpha on 2, and that's going in the first box. And then that's times the second box. I'm going to have the square root of P hat times Q hat on N. So that's going to be the square root of our observed value of P is 600 divided by 1500. Okay, we had 600 dots in the square in the shaded area out of 1500. And they tell you this as well. They tell you it's 0.4 because that's the observed value of P hat there. So you don't need to go ahead and calculate it. It's right in front and it's right at the back there. So 0.4 times 0.6 on top of N is 1500. Okay, so that's the information that you're writing in those parts. Okay, hence calculate it. Do not waste your time typing all that into your calculator. Okay, we're just going to put it in confidence interval. How do we generate a confidence interval? We go test Z. Right, we go in statistics. We go interval. Exit. Delete all. We go option. In statistics. Statistics. We go interval Z first proportion. Interval Z first prop. Okay, and then I'm just putting the information in there. Confidence 0.99, 600 successes, or 600 in the shaded area out of 1500. And then the numbers, the confidence interval I've generated is 0.367 is less than P, which is less than 0.433. So that's our answer to part II. B part II. Okay, we'll follow along there. Very good. So, a student uses an alternative technique to calculate or to estimate the area of A and claim that A is at least 14 square units. That's the claim. They're saying it's at least 14 or larger. Provide evidence that the confidence interval that we have calculated here does not support the student's claim. They've said it needs to be at least 14, which means based on the lowest possible value of P, it would be at least 14. So we're going to say, well, let's try that out. If we take, so let's make the argument and let's write it clearly. So this is part 3, part 3. So using the lower P from confidence interval, I can have 0.367 times by, okay, so the proportion, the lowest possible value P, times by the area of the square, okay? Area of the square is 36, and I got 13.2 units squared. Okay, so based on our confidence interval, the area, the shaded area, could be as low as 13.2 units squared. Okay, I'm going to need a little bit of board space, so I'm going to rub the top off. I might clear most of it actually, if that's okay. I'll clear everything except that. Our spare board's gone missing. Okay, that should do. Because this next part, this is exciting. I really liked this question. So, continuing on. Let M be the number of points that are within the shaded region when 1,500 points are independently randomly generated within the square. So we're still sticking with 1,500. Okay, we're going to generate 1,500 again. The question is, find the smallest value of M that produces a 99% confidence interval that would support the student's claim that A is at least 14 square units. So that means, okay, thinking back to what we just did here, based on the lowest value of our confidence interval, let's call that PL, okay? The proportion at the lowest value of our confidence interval times the area, so times by 36, needs to equal 14. Okay? So this means the proportion of the lower end of our confidence interval is 14 on 36. And if you put this in your calculator, you get like 0.38 recurring. So we'll leave it as a fraction, 14 on 36. So that is the lowest the proportion can possibly be. Okay, the lowest the confidence interval for the proportion can be. And so let's think about our confidence interval then. Remember, it was 0.4 take, for a confidence interval, it's P hat take 2 for 99% confidence interval, 2.576, square root of P hat Q hat on N. Okay, so this here is the lower end of the confidence interval. And this is what it has to equal, 14 on 36. So we have P hat. What is P hat in this circumstance? Well, P is the number of successes divided by the number of trials, isn't it? We're still sticking with 1,500 trials. And we're said, let M, that's what we're told in this question, let M be the number of points that are in the shaded region. So, the value of P hat is M on 1,500. Okay? 1,500 points, let M be the number that are inside the shaded region. So we've got P hat. This is the lower end of the confidence interval, and it has to equal 14 on 36. Let's smash all of this together and let's generate an equation. So what we're going to have M on 1,500 take away 2.576 times the square root of P hat is M on 1,500. Q is 1 take P, isn't it? So we're just going to put 1 take M on 1,500. On top of N is 1,500. So this describes the lower end of the confidence interval, and we know this has to equal 14 on 36. Okay? In order to be justified in claiming that the area is 14 units. So, let's, how on earth would we find M here? Equation solver, excellent. So this is a good example where you can use equation solver, although I'm reluctant to tell you to use equation solver because if it's a polynomial, it can generate multiple solutions, as we've seen, some of you have seen in your assignment. So the safest thing to do is to graph this and then G-solve the X value when it equals 14 on 36. So that's what I've done. I've gone in my calculator, I've graphed this equation, and I'm G-solving. I need to crank the window right out. You need to crank the window right out because remember, we're doing 1,500 samples here. 1,500 samples, so that means our X max, crank it out to 1,500. X is going to be somewhere between 0 and 1,500. So yeah, if you want to have a go at this, I'll give you an opportunity to. I've calculated it already.
putting in 15,000 belt. Oops.
Damn. Right, is it X count?
Oh shit.
Oh, Roger. Yes, that one was it.
Okay, so so you can keep processing it in a second if you like, but maybe I can just explain. So in the initial experiment, right, we had 600 dots in the shaded region, and we saw, well, the area could be as low as 13.2. All right. With this new sample, we've said if we want to make that claim that there are 14, the area is 14 square units, then we need 633, we round up to guarantee that level of confidence. We need 633 dots in the shaded region. How can you check this is right? Like, let's say you finish the exam, this is an answer that you've put down, okay? Let's think about what is your claim here. Your claim is 633 dots inside the region will give you a proportion of 14 on 36 or larger. So you check. You take that number, 633, and you're putting it everywhere M is. Okay? You process that, you get something just above 14 on 36. And so you are justified in making the claim for that level. Okay. And then look, this is how they integrate different parts of exams, isn't it? You know, so we've just performed a statistics problem, and then in part C there it takes you to some integration. Okay, and that's pretty basic to perform. Even if you haven't got the stuff earlier on, you can still answer part C. Okay, even if you didn't answer any of it, you can still answer part C. Just part C sort of separate by itself. You can have a bit of a go at that now if you like. I'll put an answer up in a sec. But part C is pretty straightforward. Maybe I'll just talk about part C, part 2. See how it says, hence using an algebraic process to determine A. So this means don't use your calculator. It means process it using the fundamental theorem of calculus. All right? So it's a good problem there. I like that one.